Okay, hello everyone. This for your class at least. This is the first video that I'm posting to sort of do the hybrid mix that I was talking about in class. So, what I would suggest is that you first read through section 4.1 before you look at this video because I'm not including everything, and actually within the video I'll tell you to go in the book and copy down different theorems and things just to save time and to make sure you're reading effectively and you're reading to retain the knowledge. So this hopefully just 2 videos and no longer than 10 minutes each will sort of give an overview and give some examples and try to flesh out some of the things that the book discusses, but it's really up to you to engage with this book more, and that's sort of the purpose of why I want to try this hybrid sort of classroom with you all. Okay, so let's get started. So section 4.1 talks about functions and functions as relations. So we've already talked about what a relation is. We know different types of relation, and so for this section, the homework, and excuse my writing, I don't have my stylus with me, so the homework is here, and it's number 1, B and E, 2, the entire problem, 3, B, D, F, G, H, 4, C, number 6, number 10, and 18A. So these are the problems when you come to class on Thursday that you'll be working on these problems in groups. Okay? All right. So the definition. You all have dealt with functions before in algebra pre-calc. In terms of just looking at it from how we've been looking at sets and relations, a function is also called a mapping from A to B, and it's a relation. Okay, so it's a relation F from A to B such that, that's what that S, I think I've used that ST notation before in class, such that one, so 2 conditions, so again, this is a definition you need to remember. So in order for a relation to be considered a function, 1, the domain of F has to equal A. Okay, and notice that's different when we talked about functions before. Not everything has to go somewhere, but here your domain has to equal your entire set A. So that means everything in your set A has to go somewhere, has to relate to some other element in B. And if X, Y belongs to F and X, Z belongs to F, then Y equals Z. So that's just saying when I talk about functions, I always talk about a vending machine as a function. It's a machine for every input, you get exactly one output. So what this is saying, if you have a machine, you put in $1 and you're getting out Y and Z, they better be the same things. Okay. And so that's what that's talking about. All right. So notation, you've probably seen this before as well. F goes from A to B, and we sort of know B is our range. It's also called, it's a little different than a range actually in terms of function. Okay, so we call this our codomain. So A, that's our domain, and B is called our codomain. Okay. And when A equals B, we say that F is a function on A. So that's similar to relation if it's mapping to, we can talk in terms of mapping. If it's A cross A, then it's a relation on A. So that's similar to that. Okay. So example 1, and this one is in your book. We have the set A is 1, 2, 3, and the set B is 4, 5, 6. And we have these 4 different relations from A to B. And we want to know which relations are functions, okay? And so this is a nice example to see if you understand the definition of a function. And those 2 conditions, so remember there are 2 conditions that define a function. And if you see that number 1, which is the domain of F, has to equal A, if that's not being satisfied in your relation, that you can automatically say it's not a function. Okay. So in this example, our A contains the elements 1, 2, and 3. So what that definition means of the domain of F equals A, that means that 1, 2, and 3 needs to go somewhere, needs to relate to something in each of these relations. So let's just look to see if all four of these meet that first condition. All right. So for our 1 goes to 4. We see that, right? 2 goes to 5. So 2 goes somewhere, and 3 goes to 6. However, we also have, I should say, 2 going to 6. So it meets the first condition in the domain. Everything in the domain, in this case 1, 2, and 3, relates to something. It's an ordered pair. However, the second condition states if x, y is in your relation and x, z is in your relation, then y and z must be the same. So R1 is not a relation because it fails the second condition, right? 2, 5, and 2, 6. 5 and 6 are not the same number, okay? So this is not a function. Not a function. Okay, and we go to R2. R2, let's see, 1, 2, and 3. 1 goes to 4, 2 goes to 6, 3 goes to 5. So it satisfies the first condition, and the second condition says if x's are the same and they go to 2 different places, then those 2 places better be the same. And we don't have to worry about that, right? Because 1 is just going to 4, 2 is just going to 6, and 3 is just going to 5. So R2 is a function, all right? I'm just going to circle that to represent it as a function. R3, let's see, 1 goes to 5, 2 goes to 5, 3 goes to 4. So we're defining each element in our domain, and it goes to exactly one value. Okay, so R3 is also a function, and R4 we can tell automatically that it's not because it's only 2 elements in the relation. So that's something else you can think about in making your conjectures, is that there's only 2 elements in the relation, but there are 3 elements in A. And if each element in A must go somewhere, then at minimum, the minimum number of elements in that relation better be, right, the cardinality of A, right, which is 3. Okay, we'll talk further about that in other sections. Okay, so you may want to copy this down, pause the video, copy this down, and then play it. But definition of range, so, I said the codomain and the range are different. The range of F equals some V belonging to B, your codomain, such that there exists a U and A such that the ordered pair UV belongs to F, okay? Because remember, everything, even by our definition of a function, everything in your codomain doesn't have to get hit, is what we say. But everything in your domain, if we're talking about function, has to go somewhere, okay? Has to map somewhere. All right. We have a definition. So again, in mathematics, we use different terminologies to talk about the same thing. And this is just sort of an example. You may see this again later on in other math courses. Okay. So definition, let F be a function from A to B. Okay. And y equals f of x, we already know that, right? When x, y belongs to f. So if that's a relation in f, then y equals f of x. And in this example, y is called, so y is equal, or y is called, I should say, the image of f at x. Okay. And x is called the pre-image of y under f. Okay. An example of this, I just sort of took an example. Let f of x equal the function 2x plus 5, and f is on the reals. Okay, so that means the domain and codomain are both the real numbers. Since f of 0 equals 5, we say that 5 is the image of f at 0, and 0 is the pre-image of f under f, of 5 under f. Okay. So pre-images, you think of your x values, your inputs, and images you think as your outputs. The book, when you're reading, and since you've already read the section, they sort of not really flip, but they juxtapose the phrasing. So you have to be careful, but that's how you want to think about it in terms of image and pre-image. Okay. And note that f and g are equal if and only if f is a subset of g and g is a subset of f. Okay, and that, we've talked about that in terms of sets, right? In a relation, a function is a type of relation, and a relation is a subset of A cross B, right? So it makes sense to say if we're claiming that two functions are equal, then that means they're subsets of each other. And so this example, I believe, was in your book. F of x equals x squared. F goes from the set containing negative 2, 3. That's your domain. And then your codomain is 4, 9. And then g of x is x plus 6 is equal to x plus 6. And the domain is negative 2, 3. But the codomain is the interval is actually interval, including 0 to infinity. Okay. And it may not look as though these two functions are equal, but on this domain and codomain, if we look at the domain and range, of course, well, the domains are the same, right? They're the set containing negative 2 and 3. And so the relation of F, okay, meaning the ordered pairs that satisfy F, well, when x is negative 2, y is going to be 4. So that's the ordered pair negative 2, 4. And when x is 3, y is 9, right? Because this is our function x squared. Well, if you look at g of x, you'll get the same thing. It's the relation of g, right? Because when x is negative 2, negative 2 plus 6 is 4. So that's that first order pair. And when x is 3, 3 plus 6 is 9. So it doesn't matter that their codomains are different. What matters is if the domain and range are the same, which they are. And so therefore f and g are equal. So I think I'll stop this video now and conclude with the second video.